P-Homomorphic queries on large networks. The presenter is Professor Sourav Bhowmick.
Hi, afternoon everyone, and this work is a joint work with my research assistant Ying Long, my postdoc Hu Yang Chu, and our collaborators Byron Choi from Hong Kong Baptist University and Chou Shui Geng from Fudan. So let's begin with Bob. Bob is a biologist and a non-programmer. And a query Bob would like to ask is C. elegans, which is a kind of worm, is a suitable animal model for studying apoptosis in humans. So apoptosis is a biological process that controls cell death. So in cancer, this particular process is misregulated, goes haywire, and that's why cells grows uncontrollably. So this is a typical question a biologist or a drug developer can ask, especially when they're looking for an animal model to test their drugs during preclinical and clinical trials. So Bob, being a biologist, has knowledge about the fundamental issues related to this problem. So a C. elegans is going to be a suitable model if its genes are related to apoptosis, behave similarly to those that are in humans. Second, although they may behave similarly to humans, that does not mean they are exactly the same. Due to evolutions, their behavior changes over time. And lastly, in conserved biological processes, interacting genes pairs are typically in close proximity. They can't be very far away from each other. So Bob has access to the C. elegans protein-protein interaction network, and the color-coded genes are the ones which he's interested in. Now, if you can see the structure of this particular, these 4 genes, the corresponding genes in human pathway or human apoptotic network is the one which is the same color corresponding to the C. elegans apoptosis pathway. So BID is homologous or similar to EGL1, CED9 is homologous or similar to BCL2, and so on. So Bob would like to see whether this particular substructure occurs in human pathway. I mean, this occurs means this C. elegans may be the right model for testing drugs and all the exploration they want to do. However, as you can see, there is no match for this query. This is because for conservation and for evolution, if EGL1 and CED9 may have a direct edge in C. elegans, does not necessarily mean that there will be a direct edge in BID and BCL2 in human apoptotic pathway. So the connection between BID and BCL2 is through a path of LEN2. Right? So because of these evolutionary features, they will be close to each other, but not necessarily having direct edges as you can see in C. elegans. So what Bob wants to do is to have these constraints on the edges. And there's a pair of integers which basically says the upper and lower bound of the length of the path. So BID and BCL2 should be connected not more than of length 2, and so on. So basically in this case, the query is going to map a query edge to a bounded path length in the data graph. So we call this query as bounded 1,1 P-Hom query, in short BPH query, and you can see 2 results of these queries. Okay, from the graph you saw. Now, if this query looks very similar or very familiar to some of you, it is indeed so because this is derived from 1,1 P-Hom, which was introduced by Fan et al. In VLDB 2010. What differs here is, in case of mapping edges in a G to a path of arbitrary length, we are mapping it with a bounded length. And second, instead of matching vertices based on vertex similarity, we're basically matching based on label equality. Okay, so once again, let me recall that Bob is a biologist, he's a known programmer, he basically hates to write code and wants to avoid it at all costs. So Bob wants to formulate this query using a visual interface by simply drawing the query. So in this paper, we discuss, or this paper makes this following contribution. We introduce the visual BPH search problem family, and then we provide a framework called BOOMER to address this problem. We discuss data structures and indexes used to handle or evaluate these queries efficiently. And the key hallmark here is, as the query is being formulated visually, it is also being processed simultaneously by exploiting the GUI latency. Then we discuss a little bit about result subgraph, how result subgraphs are generated from the data graphs. We will skip the visual query modification in the interest of time. You can see the details in the paper and highlight some of the experimental results. So let's start with this problem. So given a BPH query, visually constructed on a visual query interface, and a data graph G, the goal of visual bounded 1-1 P-Hom search problem is to retrieve all bounded 1-1 P-Hom matches of Q from G by interleaving the formulation of the query to processing of Q. So let me give you a feel of this by showing you what this BOOMER framework does with a short video. So here we are using Bob's query, the same one we discussed before, and the user is now, let's say Bob is now constructing the query on the visual interface, and it is querying against a data graph with 20,000 nodes from BioGrid, which is downloaded from BioGrid. It's a real data graph, and more than 2 million edges. And as you can see, when Bob is constructing the query, what is happening at the back end or under the hood is this: the query is already start being processing based on what Bob is drawing on the interface. And as you will see soon, that once the query is completed, you will get results in a flash. So as you can see, you can get the results in a flash, and then you can see the part of the network which matches this particular query. And the highlighted nodes are the nodes which corresponds to the query vertices, and shows a subgraph which contains these various vertices as well as satisfies the distance constraints. Okay, so this is what BOOMER is. So let's see what's under the hood. So the BOOMER framework has two components. In the offline component, we particularly take the data graph and extract two things. First is we construct the prune landmark labeling index, or the PML index, which was a Sigma 2013 paper, which allows you to compute quickly shortest path distance, exact shortest path distance. This is based on 2-hop cover. We also compute something called an average edge processing time. And this particular time we are going to use later to decide when to process an edge drawn by a user. So how do we compute this? Basically, we select 1 million randomly, we select 1 million distance queries between vertex pairs on this network, execute them and take the average value of the execution time. So this is pre-processing done once for a particular data graph and can be done within minutes. The next is when the user starts drawing a query. So when users start drawing a query, we start getting the matching vertices and construct an index called cap index. And this cap index basically have the matching vertices as well as the edges in this particular index. Tells you that, for example, V1 and V5, there's an edge because these two vertices satisfy the upper bounds constraint on the corresponding query edge. So all those, there is an edge in this particular cap index graph if they satisfy the upper bounds constraint, not the lower bound constraints, the upper bound constraint. And then as you keep drawing it, this index gets constructed and maintained. And when you click the run button, once you finish formulating a query, the index construction is completed and you get the list of instances of matching vertices which satisfy the query. So here is a challenge. We are not dealing with small graphs, we are dealing with large networks. So if you try to visualize a large network, it looks like a hairball. So if you're going to color code your results there, it makes no sense to users. They can't see anything. So what we do is we let users to see small regions of the network which contains the results. So a user can select from here the set of vertices he wants to, the set of results he wants to see. So he can pick up one result, and when he pick up one result, we construct the results of graph, which matches this query by using the indexes, as well as we check the lower bound constraints. So we only check the lower bound constraint at the end, not during the cap index construction. Okay, so this is the overall framework of BOOMER. Now, let me go a little bit of detail on this cap index construction and show you with an example. So we have two strategies in the paper to construct the index. And the first one is pretty intuitive, and I'm sure many of you can get this, is just construct based on the order in which the edges are drawing. So process each edges in the order it is drawn, and for every edge we construct the cap index. However, it's pretty easy to see that this idea is effective only when you can process the edge within the GUI latency, typically around 2 seconds of drawing another edge. But when the matching vertices is large or the upper bounds are large, distance upper bounds is large, in this case, it may take much longer than the GUI latency. And the results will be that it's going to be taking long time to process the edge and have a cascading effect which delays subsequent processing of the query edges. So expensive, we call them expensive edges, and they may take significantly longer than the GUI latency you get, typically in this case. So to alleviate this problem, we define another strategy called deferment-based strategy, where we defer processing of the expensive edge at an opportune time when it is good to process. Now, what is an expensive edge? The way we define is that if the upper bound on the query edge is greater than or equal to 3, and the average estimated time, remember the one we computed before, is greater than the latency of the GUI. I'll show you with an example how to do this. So TS is basically the size of the matching vertices on both the query vertices for a particular edge times T average, which we computed earlier during offline processing. And what is the latency of the GUI? In a paper, we showed that the minimum GUI latency is typically the time to construct or add a vertex or edge graphically. Now, based on this, we have two strategies. So we can defer to run. That means when the run button is clicked, then only we process the expensive edges. That means after the run button is clicked means the user has formulated the query, and we process all the expensive edges after that. Or, more interestingly, we defer to a state where the GUI is idle. No action is going on, and maybe this is the right time to process the expensive edges because we have time to do that. So the details of all these strategies are given in the paper, but I'm going to pick up one of them, which is defer to idle. So let's see how it works. Again, I'm use an intuitive example to illustrate it. Formal algorithms are in the paper. So let's say the T average for this particular network is 0.2 seconds. Now user draws one vertex, and we get the matching vertices. Okay? Then user draws the second vertex, we get the matching vertices from the data graph. So A and B, user draws an edge with upper and lower bound constants, 1 and 5. Now we decide what we're going to do. Are we going to process now? So you can see here, number of vertices of type A is 4, number of vertices of type B is 4. So here the upper bound is greater than 5, and TS is 4 times 4 times T average, which is 0.26. So it is 3.2. The latency of the GUI is 2 seconds. So it is greater than the latency. Don't process now, defer it. So we keep it in a queue or in a pool. Then the next vertex the user draws is E. So again, correspondingly, we get the matching vertex V12 from our data graph, which matches this vertex. And when the user draws an edge here, let's say with the bounds 1 and 2, in this case, the upper bound is less than 3, so we don't have to worry about it. We can process it. And you can see, because V5 and V12 is connected and satisfies the distance of their length is between 1 and 2. As you can see from V5 and V12, there's a direct edge. So there's an edge from here. Okay? And we can remove V7 because it does not satisfy the lower bound, the upper bound constraints. So next, we go ahead and construct the next edge. And we again go ahead and see which of the vertices satisfies the distance constraints. And because V1 and V12 are connected directly, rest of the vertices are not, we remove them. Now we see whether we can process the expensive edge. Now you can see TS has gone down. It's 1 times 3 times 0.2, which is 0.6 seconds. So we have, and we assume that we have enough time after processing the edge here. So we can process it now. So we process it when it's idle and finish construction of the cap index. When let's say the user clicks run now, we basically have the cap index ready. From here, we enumerate all the matches from here. We want all the instances of the matches of the query vertices. We reorder query vertices based on their increasing size of the VQIs. And then these results are shown to the user. When user picks one of them, we construct the result graph involving this, results graph involving this vertices. And in this case, we use a PML index to traverse this according to the reordered matching order, and then construct the subgraph from here. And here we only check the upper bound. Now, note that we don't have to check the upper bound if it's 1, because when it satisfies the lower, here we check the lower bound. We don't need to check the lower bound when it's 1, because when the upper bound is satisfied, obviously the lower bound is satisfied. So only we check the lower bound for the case where it is greater than 1. And in this case, we don't have to worry about it because all the lower bounds are on 1, and we show the results accordingly. In the paper, we discuss how to check when the lower bound is greater than 1. So this is the idea. Let me give you some experimental setup here. So we tested with several networks. We tested with several query sets, and we have basically 103 unique BPH queries. There were 20 participants. Queries are formulated 4 times per query and by 4 different participants. Average time taken to the T latency was 2 seconds. And we compared these 3 strategies with BOOMER unaware baseline, where basically you get the entire query first and then execute it using the PML index. So no blending of query formulation and query processing. And as you can see from the results here, if you compare to the baseline, we are orders of magnitude faster, and the deferment-based strategies are much better than the immediate construction strategies. Also, if you can see, as we increase the baseline, as we increase the upper bound, the performance, the time taken to get the results also flattens out because of 2 reasons. One, due to the pruning of the vertices in the cap index, as well as the small wall phenomena. There are very few nodes which has high distance between them in scale-free networks. Lastly, you can see the cap construction time and the size. As you can see, the size is pretty modest. For all these networks, we can easily have the cap index construction time around 100 MB. And the deferment-based strategy has a better cap index performance compared to the immediate construction strategies. To conclude, basically the idea here is, if you want to take away, is that why do we wait when query is being formulated visually? So as BPH query is getting formulated, we start processing it, and because of this, we get faster response than if you have simply waited for the entire query to be finished and then executed. So there was a tight integration between HCI and query processing. So we make the following novel contribution. One was the novel deferment-based strategy and how we blend it when visual queries are formulated together and they are processed along the way. So that's all for me. Thank you for your attention. I hope I haven't got you here. And a shameless advertisement, if you want to get a broader picture, this is a book which is being sold, or which is going to be sold very soon, by Morgan Claypool, written by us and the session chair. Yes, sure.
So, not sure if I, was, if I missed something, but my question is, the reason that you can defer the evaluation of certain edges to later, is it because the intermediate results will have an impact on how the users formulate the query?
No,
Because
so you,
if it doesn't have an impact, then you can just keep running the query, right? The order doesn't really matter, because as long as at the end you show the results, it should be fine.
so the impact is on the time the user has to wait to get the results. So imagine if you have an edge which takes a long time to process, and let's say you draw it first. What happens is you can't process the other edges which is being drawn because these two are happening parallelly until you have finished processing the first one. So because this is taking a long time, it's going to delay all the ones which you are drawing.
But to the user, if I'm formulating the query, I don't really see that impact.
You see the impact in terms of response time. So the time you wait to get your results is definitely faster than if you have simply allowed the order in which the user is formulating the query, if you process that. So for the user, it matters is how long they wait. They don't care what's happening inside. And you want to reduce that.
Any other questions? No?
Okay, thank you.
Just